Okay, so let's start. Uh, so how we will go through these sessions is that I will discuss the previous year assignments of the weeks which have been covered till now, and and during that process we will also go through the concepts which are relevant to solving those questions. And in case of any doubts, you just interrupt me in between, and you can ask your questions. Right. So till now there have been few introductory lectures and lectures covering the very fundamentals of robotics. So the course is advanced robotics, but we need to first brush up on the fundamentals of intro to robotics, and then we move ahead to more detailed and intricate concepts. So the first assignment, which I believe this time also would be uh, on these things only. This has a very general knowledge kind of a questions and a few questions towards the end relating to basic concepts of degrees of freedom and position vector and transformation matrices. So let's just go through them. So the first question says, who coined the term robotics? And yeah, so the term was coined by Isaac Asimov, as you would have known, right? So let me admit people. So to those who just joined, we are going through the assignments of last year, which will help you to solve the assignments of this year and also help clarify the concepts which have been taught in the lectures of week 1 and week 2. Yeah, so the term was coined by Isaac Asimov. So the correct option here is Asimov. The second question deals with Industry 4.0 and what it covers. So, Industry 4.0 is a term which you would have been hearing quite frequently in the recent days, and it basically involves what is called as cyber physical systems that interconnect machines and machines. I don't know why it's been worded like that, but yeah, so basically different machines interacting with each other through what is called as Internet of Things, right? So that is how Industry 4.0 is envisioned. Now, in the yeah, someone has a question?
Uh, yes, sir. In the second question, sir,
Mm-hmm.
which we just discussed now,
Mm-hmm.
shouldn't AI be included in the Industry 4.0, sir?
Yeah, I think so. Yeah,
Yeah. Okay.
possibly. So let me correct this. Good that you pointed out.
Yes, sir. So fourth option,
Yeah,
sir.
yeah,
Okay.
right. So next one is the definition of a robot, and in the lectures it was mentioned that there is not a very well defined, agreed upon, unanimous definition of a robot. And so basically there were few criterion which were given, and it should satisfy some or all of them, right? So interact with the environment, move around, sense the environment, and display intelligent behavior, reprogrammable, follow human instructions. So yeah, so here I think the best option would be option B, to move around, manipulate, sense, and displace intelligent behavior. Again, intelligent behavior is also a very broad term. Uh, so, yeah, I mean, these were just not very technical questions. Now, coming on to the degrees of freedom. So, degrees of freedom of a prismatic and a spherical joint. So, prismatic joint, as you know, is like a so a bar moving inside a rectangular slot, let's say. So there is only 1 degree of freedom in these kind of joints. So this is the prismatic joint, and yeah, spherical joint, it's a little bit harder to draw. I will try. So basically a ball and socket kind of a joint, like the ones which exist in our shoulder joints. So they have possible motions in all three directions. So the degree of freedom is 3. So the correct option would be 1 and 3. The fifth question says a mobile phone is kept on a table, and how many degrees of freedom are required by a robot to pick it up and keep it another place on the table? So how we can think of this is that since we are moving in three-dimensional space, 3 degrees of freedom would be required there, and in order to pick it, it requires one more degree of freedom. So that's the 1 degree of freedom of the gripper that would be there. So total 4 degrees of freedom would be needed, right? So if you envision it, it would be like 1, 2, 3, and a gripper. So something like this, and gripper would have a TOF to close its grip basically. So 4 degrees of freedom are required. The work volume. So work volume is the concept basically to describe what volume in the three-dimensional space a robot or a manipulator can cover. So end effector, it can reach in that volume. So for different robots, the shape of the work volume is different, right? In a very 2D case, let's say, it would be workspace or work area. Let's say for a we have these are reference axes I'm drawing. Let's say we have a two-link manipulator and just confined to the 2D plane, right? So and these are not of, let's say, equal length. So if L2 is smaller than L1, then the work volume is an annulus or a ring, right? So I guess you are familiar to these concepts. So yeah, again, for simpler systems, you can just visualize it geometrically or think of it. For more complicated systems or unseen configurations, you might have to do some mathematical analysis to exactly exactly get an analytical expression of the work volume. So for the robot having 4 prismatic joints, it's of equal length. So they are prismatic joints and equal length. So obviously it will be a cube. Now the position of a point is represented by 3 coordinates x, y, z, while orientation of rigid body is represented by uh, a rotation matrix, which is a 3 cross 3 matrix, right? So the so orientation is or handling or doing operations on orientation is not as straightforward as doing operations on positions, because position is a you can just express as a vector, right? A three, let's say in 3D coordinates, a 3 cross 1 vector, right? And we are very well acquainted with doing operations on vectors like addition, subtraction, dot product, cross product. So all these kind of operations we are very familiar with. But orientation, if you study more detail, it's actually what is called a rotation tensor, right? And it has very specific, I'm just writing a very standard rotation matrix of rotation about the z-axis about an angle about by an angle theta, right? So these kind of matrices are rotation matrices which have very specific properties. And yeah, this double, so in like the notations which I am used to is small alphabet, lowercase alphabet with a bar below it is a vector, and an uppercase alphabet with 2 bars below it is what we call as tensors, right? And the rotation tensor has very specific properties. It's like R transpose is its transpose is inverse, right? So and so which implies that R transpose R is identity, right? And such kind of matrices which satisfy this kind of relation are called orthogonal. So it's orthogonal. And so orthogonal matrices have, again, you can prove it with not a very elaborate proof, that the determinant of an orthogonal matrix, let's say Q, is plus or minus 1. And in case of rotation matrices, the determinant is, which in fact is the next question. So determinant of the rotation tensor is it's defined is that it's always plus 1. So in any calculation anywhere, if you are calculating a rotation matrix and you just want to verify if your rotation matrix is correct or not, so one check could be this, that you find the determinant and see if it's 1 or not, right? And the other option so yeah, this is a very common check that you can use. So yeah, we discussed the next question also, that determinant of a rotation matrix is equal to 1, which you can see from this example. So you can see that det r, let's say if I write for that matrix, is cos theta minus sine theta and sine theta. So this is cos square theta plus sine square theta is equal to 1, right? So even if you like multiply those matrices and you get a new rotation matrix, this property should be preserved, right? So that's why rotations are handled carefully, because doing straight away doing operations like uh, let's say we just add to rotation matrix, then it is not guaranteed that it will be a rotation matrix, right? So we have to be careful there, that what operations we are doing and whether the result is a rotation matrix or not. So like, I'm not going into much detail of that here, but just to briefly touch upon, you can see how to, you can read upon it if you're interested, how to like find difference between two orientations. So it's clear that rotation matrix we are using to describe orientation, right? So let's say if a body's initial orientation is R, denoted by the first rotation matrix R1, and the other one is denoted by R2, then it's not that the difference between these two rotation, or the by how much angle we rotate so that we get from R1 to R2, it's not that we do R2 minus R1. So this is not correct, because this does not preserve that property of that the resultant matrix should also be rotation matrix, it should be orthogonal, its determinant should be 1. So this is not done by subtracting them. There is something called as log or exponential map. So you can read up on this if you're interested. Maybe it will come later in the course. I'm not entirely sure, but it's interesting, like how to describe the difference between two orientations. And this occurs quite frequently, like if you going ahead in the course, when you study about control, so you try to let's say there is a robot and you want to keep it steady at a certain orientation or follow a certain orientation, right? Then you would use some control law to make it follow that reference orientation. And we use, maybe you are familiar with PD control, you know. So in that, let's say if you want to keep it at a certain position and orientation, let's say there is a drone and you want to keep it at a certain position and orientation, so the position part is easy. Position part, you just you do the difference of the actual position and the desired position and the actual velocity and the desired velocity, right? But so the linear part is quite straightforward, but the orientation part is, you cannot just write that the actual rotation matrix minus the desired rotation matrix, right? This is not correct, right? So in these this is a place where you these kind of situation arise. The need of defining the difference of two orientation arises in these kind of situations, which are pretty widely used in control. Okay, so more on that later. Continuing ahead, so the next question is about transformations, right? So we have a frame B which is rotated by 60 degree about z axis of a fixed frame A, right? So frame A is fixed and frame B is being rotated about the z axis of the fixed frame. So while dealing questions about of rotations and rotation matrices, you have to very carefully see which frame is being rotated about which frame, right? So which is the fixed frame, which is the rotating frame, because that your answer can be uh, inverse of what the correct answer in that place would be. So you have to be very careful there. So what we have been given is the coordinate of point P in B. The rotated frame is given 1 1 1. So find its coordinate in frame A, right? So we have two frames. Let me draw them. This is X, this is Y, this is Z, and let them, I will give them a subscript to denote which frame it is. So this is the A frame which is fixed, and about the Z axis we rotate by 60 degrees. So we do a positive rotation, that is rotation in the counterclockwise direction by 60 degrees. So as you would guess, the rotated frame would be like this. This is XP, this is YP, and since the rotation is about Z axis, the Z of both A and B are the same, and we rotate by any angle theta. Here theta is 60 degrees, so theta and theta, right? So if we draw, I drew it in a 3D space. If I just draw the same thing in a 2D space, so it would look more familiar, that there is the fixed axis XA YA, and then there is the rotated axis YB XP. Now even though you would be very easily getting the answer to this question, I would like to spend some time here, to demonstrate how do we get the rotation matrix, and basically whether multiply with R or multiply with R transpose. So that is something which is confusing sometimes, right? So let me just make some space here. How do we move it? Okay, let it be. Yeah. Okay, so we got some space. So let's spend some time on this. And here is our point P. So the point P is same, right? Point P is not changing. The description physically it's not changing. The coordinates or its description depends on the frame from which we are writing the coordinates, right? So that will change. So the coordinates of point P in the B frame, which I am denoting by the superscript here, is 1 1 1. Okay, now so in this diagram, let's say we make a construction. Now before starting, so since I mentioned and you see that the z axis of both are the same, so the z coordinate would not change, right? And you can see from the options also that the z coordinate is in the frame B was 1, and in the frame A, which are the options, and they are also 1, right? So the axis which remained the same, the coordinate about the along that axis would not change, right? That's expected. So the only change would happen in the x and y coordinate, right? So for this sake, I am just leaving out the z coordinate and writing it xy. Okay, so here xy I am writing are the coordinates of point P in the B frame, right? So I should, okay, let me make it like this. So because I'm trying to walk through a general example rather than just writing the answer to this question. So let the coordinates of point P in the B frame be xy and z, which does not concern us because z will be same. Okay, so let's draw this clearly here once again. Yeah, any doubts anytime, please go ahead and ask. Or if you're finding this very easy, then I would say that why not revise it once again. Okay. So in the B frame, which is the rotated one, the coordinates of point P is x and y. So the length of this rectangle is x and the height is y, right? Because this is where the point P is. Now let's do some basic geometry. And what we need to find is what's the x coordinate of this point in this frame, right? So let's mark it as x0 or xa, right? And this is x. So, and this will be, if we draw perpendicular from here to the y-axis of the A frame, so this distance would be ya, right? So we have to find xa and ya in terms of x, y, and the angle that we have, the rotation angle theta. Okay, so let's do some geometry now. So how will we get x? Let me draw a line. Okay, someone's here. So this line, let's draw it here. So this distance, right? Let's mark triangles. This is O. Let's make it P, and this is Q. right? And this is n. Okay, okay, p we already have, so make it let's say mm, let's make it as b, but don't confuse with frame b. So in triangle OBQ, OQ is x cos theta, right? It's x cos theta. And to get what we need to find ON, right? Because ON is XA, and that's what we need to find. So XA is ON, and ON is OQ minus QN. So OQ we know, and QN we want to get, right? So how to get QN? So if you see, QN is this. Let me use another color. It is getting little cluttered in here. Oops. So this line which you see, right? So this line which you see, the red line, is same as QN, right? So what is QN? So in that triangle, I'm again not naming it because it will be too many alphabets, but this PB and this right angle triangle, what will be the angle? This angle, right? So this angle would be, if you see, like this is theta, and this line is parallel to that, so this is also theta. Okay, so that length of that red line segment is y sine theta. Okay, so XA is x cos theta minus y sine theta. So here we have the first expression relating the coordinates of point B in the B frame, which is x and y, and the rotation angle. So we can very easily compute what is XA, right? Similarly, if you do similar constructions on the about the y-axis, we can get YA. So let's do that. So for YA, we need this distance, and the first distance that we can get is, let me again use a different color. So we have x here, and let's draw a segment here. Okay, so basically from this point, mark this point as Z. So this is O, this is Z, and let's mark one more point as maybe N. So right, so YA, the coordinate which we are interested to find, YA is ON, right? And I used here also, so yeah, please don't get confused, but we are talking about the annotations on the y-axis right now. So YA is ON, and that is equal to OZ plus ZN, right? Now OZ, what is OZ? OZ is in that right angle triangle which I drew here with this blue line. So the hypotenuse is x, and this angle is 90 minus theta, or this angle is theta. So x sine theta, right? So OZ is x sine theta. And Zn, what is Zn? So Zn is, yeah, Zn is this vertical side of this triangle, right? This one. So this is y cos theta. Okay. So y cos theta. So ON, which is YA, which we are interested to find, is x sine theta plus y cos theta. Okay. And there we have it. So we have both xa and ya in terms of x, y, cos theta, sin theta, right? So if I write it now in the usual form, so xa, ya, right? And again, if I write it in a more succinct manner, this is the coordinates of point P in A frame is equal to, first let me write the entire expressions again. So now since we are writing these kind of expressions again and again, for cos theta I will write c theta, and for sin theta I will write s theta. So x cos theta minus y sin theta and x sin theta plus y cos theta. Okay. So, and now since we have x and y in both the rows, we can write it as a multiplication of a matrix, right, and a column vector, which is x, y. And what are these quantities? This is a rotation matrix from the B frame to the A frame, and the column vector is nothing but the coordinates of point P in the B frame, right? So very in a concise way you can write this. Okay, so this is the process basically, and so this is just to give you an idea that these things are rooted in the very basic geometry, right? But since the rotations do get very complicated, especially in 3 dimensions and successive rotations, so we can't always derive from first principles, right? So we use directly right rotation matrices of the transformation and multiply them accordingly. So in this case we have PB, right? We have, let me write it here, we have PB, and the rotation matrix that will take it to A frame will be, here theta is 60, so cos 60, which is half, minus sin 60 root 3 by 2, again root 3 by 2 and 1 by 2, and since we are taking all three coordinates, so this, right? So you multiply this matrix to this vector and get the answer, right, which is with the coordinates of point P in the A frame. So I believe the only thing which remains is to multiply these two, and that you can very well do.
Sir,
Yeah.
I have a small question over here.
Mhm.
Like here, it's a small thing, sir.
Mhm.
Then you have marked a red color line over there, no, sir.
Mhm.
In
Mhm.
there, how did you get theta, sir? Which theta does it how did we get theta over
Okay,
there, sir?
okay. So
I'm sorry.
yeah, so
Yeah.
let's say these two thetas, because you are clear, right? Because we rotated by about z-axis. So the
Yes, sir.
x will be rotated by theta, right? The first diagram which we drew here, right? So the angle
Yes,
between the two x-axis or the two y-axis is theta, right? So now let's just follow the angles. So this is theta, so this will be 90 minus theta, right?
yes, sir.
This is a 90 degree, okay. And then let's follow the angles. Okay, so this is theta, so this will be theta, alternate angles. These
Yes,
are
sir.
parallel lines, so this is theta. Now once this gets theta, so now this is 90 degrees, so this is 90 minus theta.
Which
And
is 90 degrees, sir? That
yeah,
PB
this,
is 90.
yeah,
PB.
so
Okay.
PB and O, the angle
Oh,
PBO
okay.
is 90 degree, right? Because we
Okay,
are
okay, okay.
we have
Yes, sir.
dropped a
Yes.
perpendicular to get the coordinate of that point, right?
Okay, okay.
So that is 90. So
Okay.
this angle will be 90 minus theta. Let me zoom it a little bit, right?
Okay,
So
okay. Okay.
the angle here is 90 minus theta, and since this is a right angle triangle again, so this angle is theta.
Okay, sir. So angle PBO is 90 degree. Okay,
Yeah,
okay.
angle PBO is 90 degree, because
Okay.
right, if there is a point and you want to get the coordinates of that point, so you draw perpendicular, right, on the both axes. So this is the x coordinate, this is the y coordinate, right, if this is a point. So yeah, that's why.
Okay. Yes, sir. Thank you.
Okay, cool. Okay, now the next question is has one more layer in it, right? So in this question, the frame B was just a rotation away from frame A. Now in this question, we have a rotation again of 60 degree, this time about the x-axis, and then the there's also a translation, right? So a frame B is rotated by 60 degree about x-axis of fixed frame A and translated by this much amount in the xyz direction of A, right? So the origin of A, right, in this question, the origin of A and the origin of B were coincident, right, after the transformation. There was no movement of the origin. So until there is a translation, the origins will always be coincident, right? But in this case, we are also doing a translation to the frame B. So the frame B is now not coincident with frame A. The origin is at a distance of 111 units from the origin of frame A, right? So now once we have both rotation and translation, so the transformation, we can do it like step by step also, but you would have studied in the lectures that there is something called as a homogeneous matrix, right? A 4 cross 4 matrix that we construct to basically do the entire transformation in one go. Like one matrix multiplication gives the uh, rotate the transformed coordinates. Basically, we can't say rotated because there is a translation also. So let me draw the scenario here. So let me keep it, so again let's keep it xa, ya, za, right? So let's do the first thing. First thing is rotated about x-axis by 60 degrees. So now it's the x-axis which will remain the same, the intermediate frame. Let's do one thing. There is frame A, then there is, let's make an intermediate frame C, and then the frame B, right? So we will do this in two steps. First, there is a rotation about x by 60 degrees, and then there is a, let's say, a translation by the required amount, right? So this is our the two concerned frames. I'm just introducing the C frame for explanation purposes. So for frame C, the x-axis will remain the same because that's the axis of rotation, and the z and y will change. So, and we are rotating again 60 degree in the positive direction. So the y will come somewhere here, z will be somewhere here. So this will be zc, yc, right? This theta is 60. This is also theta. Okay. So till xc the scenario is same as the previous question. Now let's mark the origins. So origin of A and origin of C are the same. There is only rotation till now. Now after that we also translate, and translation, the units of this vector, you have to note that it's given in not the C frame, it's in the A frame, right? In the original frame, the fixed frame. Okay, so you have to, it could be that the translation this units of translation are given in, let's say, the rotated frame, the C frame. So there you have to be careful. So now the translation, so basically the scenario will look somewhat like this. Again, this is not accurate, but just for understanding purposes, and it will be like the original frame, let's say somewhere here. So this is frame A, and there was frame C, but we moved, and now we are frame B. So this is origin of B, this is origin of A, and this vector which I am drawing here, right? This, and let's mark it OA. So this is the translation thing. So origin of B minus origin of A is 1 1 1. Okay, so how to proceed? Okay, let me make some space. Excuse me. Okay, right. So now how do we write for a general rotation plus translation case? How do we write? Okay, got some space. Yeah, so a transformation matrix, which we denote by T, is what we call as homogeneous transformation. So a transformation matrix from B to A, right? Because again we will have to find the coordinate of the point P in A frame, right? So we need transformation from B to A, right? So it's a 4x4 matrix, and the bottom row is 0 0 0 1. Now these two blocks, so this block is the rotation part, right? Rotation from, oops, yeah, it should be, yeah, right, about whatever angle. And this is origin, the position vector of the origin of B frame expressed in A frame, right? Very important, that in which frame is that quantity expressed in. So it should be expressed in the A frame to which we want to convert, right? So this basically, you can quick sanity check would be that all these frames in the superscript here should be consistent. So now we know these two quantities individually, right? We know that the rotation matrix from B to A.
Sir,
Yeah.
uh, here, sir, in the last row, sir, last row of transformation matrix,
Mm-hmm.
why do we need a perspective and scale, sir? Like in the lecture, it was just mentioned as that 000 is perspective and
Mm-hmm.
1 is a scale. What is the purpose, sir? Like we have rotation and we have translation now.
Mm-hmm.
So
Right.
why
So
do we need this?
yeah. So right. So firstly, you should understand that uh, these two things are also useful, right? Perspective and scale, because those are also two kind of transformations which we can do, right? Let's say we are a vector, we are rotating it, we are translating it, and we are also scaling it by a certain factor, right? So again, it is borrowed notation, I think, from, you can say, perspective scaling is usually used in, when we are working with cameras and all. So there I think this is used. I have encountered this where these values are also changed. But mostly in robotics or these kind of applications, we do not do any perspective or scaling transformations. And again, another thing is, so yeah, so those two things are devoted to that part. And also, like, mathematically also you can think it as, we want to make it as a square matrix, right? If this is not there, this will be a three rows and four columns, right? 3 cross 4 matrix. So operating with rectangular matrix is not easy. Like, we can't take inverse, we can't do those kind of operations. Here, if when we make it 4 cross 4, we can easily take inverse of this. Of course, it's not directly inverse of this. We invert each of them individually. But yeah, I think in the purpose here will not be very much clear, but in a different application, this is used. That's what I recall at the moment, in especially in working while with cameras and all, where there is some magnification and there is some perspective. So then these entries are non-zero.
Sir, so yes, sir, I got what you
Hmm.
meant, sir.
Mm-hmm.
Uh, Here we have taken scale as one, no, sir.
Hmm.
Uh,
Hmm.
by scale, here it means normal measurement, no, sir. Like in graph, we have that scale, no, sir. That scale and this scale is same, sir.
By scale here means, the scaling is means that the length of the vector will be preserved,
Okay,
right?
okay.
So
So
let's say the so length you can get by taking the norm of the vector, right? Let's say x square plus y square plus z square under root gives the distance from the of point xyz from the origin, right? So let's say if then yeah, so that's the thing. Basically, if I make it 2 here, so then the vector is rotated, translated, and also elongated.
okay, magnitude is increased or
Yeah,
decreased.
magnitude is increased to
Okay,
that,
okay,
multiplied by that scale.
okay, okay, okay. If we take zero, it will become not zero vector, no, sir. I mean, it totally
Yeah, yeah,
becomes.
yeah, then it will vanish, so you
Oh, okay,
won't get anything,
okay, okay, okay.
because it
Yes,
will, the last row will entirely be zeros.
zero.
So when you
Yeah,
will multiply it.
it will become zero, but I mean, it will become 4 cross 4 matrix, but still, practically, we won't get any vector.
Hmm.
We
Hmm.
won't exist.
Hmm. Hmm.
That's what we can
Hmm.
say, no? Sir?
Hmm. Hmm.
Okay, okay. Yes, sir. Yes, I got it, sir.
Okay, so yeah, so the rotation from B to A about the x about 60 degree, and this is straightforward 1 0 0 0 cos 60.5 sin 60. So write the same values, so you get this, and this translation part of what's the translation of origin of B is 1 1 1. Okay, so the full homogeneous transformation matrix will be 1 0 0 0 0. Those values, again I'm not writing them again, but and here 1 1 1 0 0 0 1. Okay, so this will be the transformation from B to A. Okay, and yeah, so and while transforming, since we have made this as a 4 cross 4, so we will have to add one, here. So this will be a 3 cross 1 and then added 1 here, then here T B, and here will be B P and 1. Okay. So by multiplying this, you would get basically the coordinates of point P in A frame. And like this is a proper way of doing it, but for simple equations you can very quickly verify that if you just multiply this point, 2 to 2 with the rotation matrix and just add 1 to each of them, then also you should get the answer, because that's what will happen, right? This, when you multiply by the rotate, so you are basically writing this kind of a transformation. So if I write here AP is, you first rotate the point, right, and then add the translation in it. Right, so this will be Rx 60 degree into 1 2 2 2 plus 1 1 1. Okay, so I mean, for understanding purposes, this will give you, this is like more clear that what you are doing basically. If you just keep on like blindly, just like in a formulaic way, if you keep on multiplying with transform matrix without understanding this, then like it's not full understanding, I would say. So what's happening, we are converting from point expressed in B frame by first multiplying it with rotation, and then translation you can just add to it. We are directly adding it because the translation is given in A frame. If it would have been given in some other frame, then we would have to first transform that translation into that frame and then add it, right? So you can verify that directly by multiplying this 4 cross 4 into this way, right? This and this should give you the same answer. Okay, so yeah, I think these are the questions for the first assignment. Any doubts still here, anyone? Okay.
Sir,
Yeah.
mathematically speaking, sir, why do we write like now this is a 4 cross 4 matrix, no, sir, transformation. While multiplying this transformation matrix, we are multiplying with the translatory coordinates, like 1 1 1 comma 1 comma 1 in this case. Like we are converting a point which is in a different frame to the frame to a fixed frame, like movable frame. We are converting it to a fixed frame, right, sir? Right, in this whole procedure. So for that, we are multiplying this transformation matrix with the with the point of this 1 comma 1 comma 1. We are multiplying. There, why did we add, right? Why do we mathematically write extra one, sir? At the end of like in the fourth row, we write one more,
Okay,
sir.
okay. Yeah, so
Yeah.
so that is just for like for multiplying matrices. Like this is a 4 cross 4, right?
Yes,
So
sir.
we have to make it 4 cross 1 in order to
Yeah.
multiply them.
Like other number, other number, why we don't write, sir,
Okay,
here?
okay.
Like
Like why don't we write 2,
yeah,
3? Yeah, that
like
no.
zero mainly.
Yeah, I get you. I get you. I get your point. Like though since if you can by knowing the rules of matrix multiplication, you that is very clear that whatever we write here does not affect this result, right? Because
Yes, sir.
right, because the first, let's say the first row we are multiplying with this column, and then the okay, so me let's say this this is point 0.5. So I'm just writing random numbers and some point, let's say x, y, z, right? And let's put anything here. Let's say alpha, some alpha, right? So what? Let's multiply it. So oh, I missed a column here, and let there be same thing 1 1. Okay, so let's multiply them. So first row multiplied with this is uh, yeah, no, 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 I think no, let's do this, we'll make it clear. So x plus 0 plus 0 plus alpha times 1. No, I was wrong there in saying that it won't affect. Okay, so if you see, so next will be 0 plus 0.5 y minus 0.8 z plus alpha times 1, right? Then 0 plus 0.8 x plus 0.5 y, sorry, z, this will be y plus alpha times 1, right? And last will be 0 0 0 plus alpha. Okay, so you see it does affect what we put there. It does affect because if we put other, let's say if we put 0, right? So then the translation part would not affect it. It's basically so when you put alpha 0 here, basically it will be equivalent to saying there is no translation,
Yes, sir.
right?
Yes, sir.
So yeah,
Yes.
it does affect. So I also missed that point. It's good that we did it. And yeah, and if we put any other alpha values, it would be like 2 times of that translation, 3 times of that translation, whatever multiple of that translation. So by modifying that alpha, let's say if we want to, by modifying that alpha, we can vary the distance of the B frame from the A frame in multiples of this translation units. So yeah, so basically since generally in problems we want to translate by the given units only, like if it's given 111, we want to do by 111, so we keep it identical. So to keep it identical, we put just 1 here. If we put 2 here, then the translation would be 222, right? And if we put 0, then there is no translation. It will be just equivalent to a rotation.
Yes, sir. To allow matrix multiplication and not to cause any change in the translation process, we just write 1. We
Yeah,
just
yeah,
put 1.
yeah. So
Yes.
to just do the translation by the
Yes.
required amount. Again,
Mhm.
you can just
Yes.
play with it,
Yes.
but yeah, it's good that you
Yes.
pointed this out.
Thank you, sir.
Yeah.
Yeah.
Okay. Okay, so in week 2, the major concept that has been discussed is the DH notation. And again, it's a very fundamental concept which allows us to write the transformation matrices, the homogeneous transformation matrices for multiple degree of freedom robot manipulators and all, right? So again, DH parameters is not something which can't be done without, right? I mean, you can still write transformations and rotation matrices and all without knowing DH parameters also, right? But knowing the DH parameters sets a very systematic way to assign axes, and sort of it's a convention. So any convention is laid upon to make things uniform, and make it a very systematic procedural way. And one thing also is that the it makes it easy to write in a very programmatic way, so that it's easy to code up things also. Let's say you want to write a piece of code which finds the transformation matrices for uh, certain manipulator. So it's good that there's a systematic way to assign axis, angles, and then transformations. So in that way, it's a useful convention to follow. But again, as you if you go deeper into rotations, dynamics, and all, you'd see that without in general without always assigning DH parameters also, you can or you can like choose axis of your own choice also and still write it correctly, right? So no hard and fast rule there. Okay, so there are now again few set rules of this convention that when followed gives us the what we call as DH parameters, right? So the first thing is that uh, as per the DH notation, the axis of rotation or translation is the z axis, right? Because generally, let's say if there is a let's say there is a 2R manipulator with a revolute joint, then the axis of rotation, this we assign the z. Or let's say if there is a and there's a prismatic joint, so and moving like this, so in this direction we will assign z of that joint. So and generally you would encounter revolute or prismatic joints, mostly revolute and some prismatic joints also. So along the axis of rotation for revolute, along the axis of translation for prismatic. That's the first convention. Now the four parameters. So what are the four parameters that we put in the DH table, right? So good time to go over them once again. So let me write it: A, alpha, D, theta, and there are names for them also, right? So this is joint angle, right? This is link twist, right? This is link length, and this is joint length. So what you would see is that this d and theta are the things which are variable, right? Because as the robot moves, the d and theta will change. So theta is non-zero for revolute joints, and d is non-zero for prismatic joints, right? So in prismatic joints the d changes, in revolute joints the theta changes. And a and alpha are the properties of that manipulator, of that specific system. So unless you are not physically changing the links and the you know the way the links are connected, these two will not change. So these are constants for a given system. Okay. So these are constants for a given system, and How to find these? So the link length is the distance between the consecutive z-axis. The twist is the angle between the consecutive z-axis. The joint length is the, again, distance between the consecutive x-axis, and joint angle is the angle between the consecutive x-axis. So z-axis and x-axis are the, by convention we are only concerned with them, right? Z-axis is generally put, as we mentioned, along the axis of rotation or the translation, and the x-axis is put perpendicular to that along the link length, along the physical direction of the link. Okay, so let's say we have a, okay, so it's here only. So again, let's work on this to further clarify the things. Okay, so let's first draw the axes. Let me use different colors. So now, okay, not like this. So this is a 3R planar manipulator, right? So this manipulator does not move out of the plane. Okay, so, and as you would imagine, the z-axis of each would be, since I cannot draw the, so this is out of the plane, right? Coming out of the plane of the paper. So this is, so z0, so first we assign the fixed frame, because in every problem there should be a fixed frame, which is a reference for all other frames, right? So generally we mark it as a 0, and the first frame z-axis is also the same. So z, and so this kind of notation means that this arrow is along the axis of both the zeroth frame, the z-axis of both the zeroth frame and the first frame. Okay, now further down the chain, this is z2, this is z3. Okay, and how to, x-axis is defined along the link length. So x01, this is x2, this is x3. Okay, so once we, and y, we don't mark generally y-axis, but y is the cross product of x and z. Okay, so perpendicular to both. Now we make a table, call as a th table. Okay, so again, there is a fixed way of writing it also, as it has been taught in books for many years. So first we write the link length, then the link twist, then the joint length and the joint angle. Okay, and for this we will have 1, 2, 3. Okay, so for the first one, right? So the first one is the a, so for I, if we put 1, it will be a0 alpha 0 d1 theta 1, right? So basically, what's the link length of the first one? Okay, so the 0, there is no distance between 0 and 1, so this will be 0. Okay, there is no angle between the z also of 0 and 1, so this will be 0. Now the x is also not changing, so again 0, but the angle between, so you would see that this 0 and 1 I have marked overlapping here, but as the link will move, the so it will like this. So x0 will stay at that place because it's a fixed, and x1 will move with the link. So if the link moves theta, it also moves theta, right? So this will be theta 1. Okay, so this is the first row, and which is the basically answer up to this question, that what's the first row of the TH table. So first row you have to be extra careful in the first row, because how you choose the fixed frame and the first frame, right? So generally they are chosen coincident in that configuration. Now the next is I is 2, so A1, so this is the distance between the Z2 and Z1, right? So distance between Z2 and Z1 is L1, so L1. Z2 and Z1 are parallel, there is no twist between them, so alpha is 0. Also the x1 and x2 are intersecting, so again there is no distance, 0. Okay, and x1 and x2, x, just wait for a second. नहीं, रुक जा, एक मीटिंग में हूँ. Yeah, so the distance between Z1 and Z2 is L1. There is no twist between them because Z1 and Z2 are parallel. The x1 and x2 axes are intersecting, so there is no perpendicular distance between them is 0. And the final is the joint angle. So the angle between x1 and x2 will be theta 2, right? Because x1 will be along the first link physically, and x2 will be along the second link. So then the angle between them will be theta 2. Okay, and now for the third one, so similarly third one will be distance between 2 and 3, so L2, twist will be 0, distance will be 0, and angle will be theta 3. Okay, so this completes the DH table for a 3R planar manipulator. Okay, and yeah, you can add one more frame here, but there is no degrees of freedom here. Then you will get L3 also in here. It will be just like, since there are no more degrees of freedom, there is no rotation here, so what you can do is basically, yeah, I mean there is no need, but you can add one more frame here, x4 and z along the same direction as 3 z4. Okay, so it's just like there is a translation to that frame, so it will be like L3 0 0 0. So yeah, I mean if you want to find the position of the end effector, if you know the position of the origin of this frame, this frame, if you know the position of the origin, then you can just add L3 to that position to get to the end effector position. Okay, so this is how you construct TH parameters. And the usefulness of TH parameters is that once you construct this, right, and which you will see later also, that now using each row, so there will be a term in lecture discussed as the generalized matrix, right? So it's basically the homogeneous transformation matrix corresponding to a big matrix. Yeah, don't try to recall it, like remember it by heart, just understand it. It's like for a given row, right? For a given row, what are things which we are doing, right? There are four individual transformations from going to one frame to other frame, right? We translate by a a1 ai minus 1, right? We rotate by alpha I minus 1. So we translate along z ai minus 1. We rotate about z by alpha I minus 1. Then we translate along x by di, and we rotate about z with theta I. Okay, so when you multiply all these, you get the transformation matrix from I minus 1 to I. Okay, so that's how you get that expression. I guess you would have seen in the lectures. So the ideal way would be to not just directly blindly remember the whole matrix, but to understand that that generalized matrix is a product of four individual transformation matrices corresponding to these uh, this translation along z, this rotation along z about z, this translation along x, and this rotation about x. So you get that generalized matrix, and once you get the generalized matrix for one row, then similarly you get for the other three rows, right? And they can be multiplied in sequence, to form a chain of transformations. Like let's say we want to go to 0 to the third frame, we write 0 to 1, 1 to 2, 2 to 3, right? So first you need to individually find out this, this, right? And then multiply them to get the final transformation. So what you will, the use of this would be, let's say something like this. Okay, so there's a, again what we did earlier, there is a point expressed in the third frame. Okay, so let's say we are expressing the end effector position in the third frame, and we want to get the end effector position in the 0th frame or the fixed frame, right? So we can use this transformation matrix to get to that fixed frame, right? And further down the, in next few weeks, or again in the coming lectures, you would see forward kinematics. So in all those things, this would be necessary. So you would frequently see this transition matrix. Again, the question 4 is for the manipulator shown in Q3, the second row of the DH table. So yeah, once you create the DH table, the other questions are straightforward, right? So this is the second row of the DH table. Okay, so any queries in DH, constructing DH table and all DH parameters? We'll stop for a couple of minutes. Just give me. Okay, so moving on, we have the a 2R 1P manipulator, right? And we have to write the, or we have to get the DH table for this. Okay, so, and thankfully the most like the the most crucial part or the crux of the problem has already been done by assigning the axis. So once the axis has been assigned, the rest things are very much straightforward. So assigning the axis is the most important step which you should give the most attention to. Okay, so but again I will go through how the axis have been assigned. So basically here we have the first rotation, this about this base it rotates, and then it rotates and then there is a basically prismatic joint here. This arms goes in and out, and finally this final gripper can rotate. Okay. So again, as I mentioned, the first frame, the 0 and 1 frame, we chose coincidentally, and since the axis of rotation is in this direction, so we chose the direction in that side. Now this is a good example of cases which arise when the z-axis of two uh, consecutive z-axis intersect, right? So z2 you assigned like this because prismatic joint is moving in this direction, and this is the axis of rotation of the first joint, and they are intersecting. So in that case, how to assign the x-axis? So x-axis is then assigned to the, so you have these two directions, so you take a cross product basically, or you choose a direction which is common normal to both of this and mark it as the x direction, right? So in this case, the 0, 1 and 2, all these frames have the same x direction, right? So so till frame 2 is done, d2 is the changing variable thing, theta 1, d2 and theta 3. And now finally this joint is again straightforward, rotation axis is this, we assign z3 along that, and since z2 and z3 are again intersecting, right? So we just choose a perpendicular to that, right? So in this case, this is a very special case. I mean, special in the sense that all the z-axis are intersecting. This is z2, 3, right? So all the x is basically 0, 1, 2, like ignoring translation, they are all in the same direction. Okay, so now let's go to the th table. Okay. So again we put I, link length, link twist, joint length and joint angle. Okay, we have 3 frames. So the first frame, let me minimize it. Okay, so for the first frame, since 0 and 1 are intersecting exactly same, so link length is 0, link twist is 0, x is also same, so 0, and theta is different, so like x1 will rotate and x0 will be in the same place, so the angle between them will be theta 1, right? Now in the second row, z1 and z2 are intersecting, so link length is 0, z1 and z2 angle between them. Now this, note this point, so alpha is angle between z1 and z2, right? And the angle is about the x-axis. Now we have, as you would see, when we rotate from 1 to 2, right, the rotation is in this direction, right, in this direction, and this is like minus of this x-axis. We are rotating about the negative of this axis, so the rotation angle will be minus 90 degrees, right? So be careful in choosing the sign of rotations when transforming between frames. Okay, so minus 90 degree. And then what's the distance between so distance between 1 and 2, so the prismatic joint will move, so that will coming inside and outside, so it will be moving, so that will be d2, and the angle between them will never change and is 0. Okay, now for third one is a simple evolute joint, since z is again intersecting, so 0, 0, right? The distance between the x, right? Distance between the x is a fixed quantity, which is L2. Okay, because L why though, so be careful. L2 and D2 are different things, like, because if you just imagine I take out this thing outside that slot. Okay, so then in that case it's a piece like this, right? The piece like this, on which I have fixed x2 here, right? So x2 is fixed on this link here, and x3 I have fixed here, right? So the distance between x2 and x3 does not change when the this part goes inside and outside the slot, right? So this is a fixed distance, which is L2. Okay, and finally the angle between the x3 and x2 will change when the end rotates, and it will be theta 3, right? So this is the DH table for this robot, 2R 1P robot. And the question is, what's the second row of the DH table? So second row is 0 minus 90 D2 0. So 0 minus 90 D2 0. Okay, this is the second option. Now the next question. So the next question is again going back to Q3, which is the 3R manipulator. This question, and they're asking what's the coordinates of the origin of frame 3, right? So again it's basically you have to repeatedly apply trigonometric quantities, or in other ways you can also do by using transformation matrices. Okay, so let's do it, right? This is pretty straightforward, that for, let's say, for a case like this, 1 2 3, okay, so theta 1, theta 2, theta 3. Okay, so no, you can do by basic geometry also without like even concerning about finding the transformation to this. Like this is L1, this is L2. Okay, and you need to find this P point. That's the origin of frame 3, right? So we have to find the coordinates of P point in the 0th frame, x0, y0. Okay, so what will be this point? Let's say Q point. So Q point will be L1 C1, right? So L1 C1 is the x coordinate, and L1 S1 is the y coordinate of Q point, right? So, and now okay, and now what will be the coordinate of the, so let me draw it one more construction here, right? So this is theta 2. Theta 2 is from L1's direction to L2, right? But from horizontal this angle is theta 1 plus theta 2, right? So maybe I will draw here once again. So basically the second triangle is something like this. This is P, this is Q, this angle is theta 1 plus theta 2, and this is L2. Okay, so the base will be, or the distance in x direction will be L2 cos theta 1 plus theta 2, which I will write like this, right, in x direction. So let me mark it as n. So qn is L2 C12 and Pn is L2 S12. Okay, so and that's what we need, right? We need, so first this distance and then add qn to it, right? So final x coordinate of the point P which we need to find is L1 C1 plus L2 C12, and similarly y is L1 S1 plus L2 S12. Okay, and that should be one of the options, and it is this, right? So pretty straightforward. Now what you should try is, get the transformation matrix from this third frame to zero frame, and basically you want to find what is the expression coordinates of the origin of third frame. So in the third frame, the coordinates of origin of third frame will be what? 0 0 0, right? So in the third frame, the point is this. We have to find what's the expression of this in the 0th frame. This we have to find, right? So what you should try is that you should write the transformation matrix and multiply it with this. So basically it's equivalent to transforming this point to the 0th frame, right? And see if this matches the answer here. That will be a good small exercise. Okay, so now again the q3, again the same question, and it's saying origin of frame 2. So frame 2 is here where we marked q, and we calculated it is L1 C1 plus L1 S1, right? So L1 C1 L1 S1, this one. Okay, now this is the Scala robot, quite popular robot in textbooks, right? And very popular in chapters concerning DH table. So again we have to construct the DH table for this robot and answer the following questions. Okay, so the remaining 3 questions are based on this only. Okay, so I guess that would be the last topic for today. So let's, again the frames have been marked, so half of our task is, like, more than half our task is already done. So let's go through the frames, right? So first frame, so there is a rotation about this, so z1 is about this. Okay, x1 is along the first link, this direction is the first link, L1 is the link length of the first link. The second rotation axis is here, so z2 is here, and x2 is along the second link. Okay, now the third rotation is around this, so z3 is along this, and x3 is, now again first, so the sequence would be that you would mark z3, then you would go to marking z4. Okay, and then you would see that z3 and z4 are basically intersecting, right? They are just in opposite directions. So x3 and x4 would be, as I mentioned earlier in Puma question, they would be just normal to z, right? They don't point physically in the link's direction. Okay, so let's start and go step by step. there are 4 frames, so we have 4 indices, and so 0 and 1, the z is the same, so 0, 0, the x is also the same, so 0, and it rotates, so theta 1. It is standard. Next one, the z is, so z2 is away from z1 by a distance of l1. Okay, now z2 and z1 are parallel, so the angle between them is 0. x2 and x1 are again, the distance between x2 and they are the same, and the angle between them is theta 2. Okay, now the third one is z3, so 3 and 2 are away by l2 x, and the angle between them is 0. Now the distance between x2 and x3, right, since x3 will be moving up and down, right, so it will be like this, so x2 will be here and x3 will keep moving up and down, so there will be a distance between them, which is d3, which is the variable, right. D3 will be changing as the robot moves, and the angle between them is 0 because x3 and x2 are parallel. Okay, and the last one, so the last one we have the distance between z is 0, right, because z3 and z4 are intersecting. Now the angle between z3 and z4, so how to get the angle? So again, if you rotate, if you keep your fingers along the x, thumb along the x, and rotate from 3 to 4, so it's positive 180 degrees. Okay, so pi plus pi, note, and the distance between x3 and x4 is again fixed, which is l4, and the angle between them is theta 4 when the wrist rotates, this gripper thing rotates, so x4 rotates, x3 stays there, angle between them is theta 4. However, the distance between 3 and 4 does not change, which is l4. So what are the variable quantities here? You mark them, right. So variable quantities are theta 1, the first joint angle, theta 2, the second joint angle, d3 third, and theta 4 fourth, right. So you should always verify, right, that if a robot is of certain degrees of freedom, here it is 4 degrees of freedom, right, then in your DH table 4 variables should be there, right. You should always cross check so that you are not missing any variables, right. And all these things, L1, L2, L4, this angle, these are all constants, right. They depend on the physical form of the robot. Okay, so the question is, what's the second row of the DH table? Second row is L1 0 0 theta 2, so this is the correct option. And what's the third row of the DH table? So third row is L2 0 D3 0, right. So L2 0 D3 0 is there, this is the right option. And what's the fourth row? Fourth row is L4, this one, right, 0 180 L4 theta 4, 0 180 L4 theta 4, right. So basically you get answers to all these questions by getting the DH table. Okay, yes, so basically we covered assignments of week 1 and week 2 of previous year. It will help you solve assignments of this year also, they are pretty much the same. And yeah, any specific questions, if anyone of you has, then please go ahead. Okay, so Okay, I think that's it from my side for today. And yeah, we'll meet next week at the same time. And the recordings and the this document will also be shared to you by the NPTEL team. Right? Okay, nice talking to you guys. See you next week.